Welcome to Unit 4, Lesson 1, Interpretations of the Derivative in Context. This lesson focuses on Topic 4.1 of the 2019 course and exam description for AP Calculus AB, Interpret the Meaning of a Derivative in Context. The standards for this lesson are CHA 3.A.1. The derivative of a function can be interpreted as the instantaneous rate of change with respect to its independent variable. CHA-3.A.2, the derivative can be used to express information about rates of change in applied contexts. In CHA-3.A.3, the unit for f prime of x is the unit for f divided by the unit for x. Our instructional objective is that students will be able to use real-world scenarios in order to determine the meaning of a derivative. Our inquiry question is, how can derivatives allow us to solve real-world problems involving rates of change? As we explore this topic, we'll draw upon our previous discussions of the derivative in its representation algebraically, numerically, and as the slope of a tangent line. In this lesson, we want to interpret the meaning of the derivative in a verbal manner as it relates to the context of real-world problems. An important part of this topic is the correct use of notation, so it's important to take a moment and reflect on the different notations that we use and where they come from. When Newton was developing his ideas of calculus, his focus was primarily on velocity. Today we know the derivative's importance reaches into many areas involving rates of change. So let's take a moment and consider the Leibniz notation one more time in a slightly different way. Leibniz stated that the variable y depended on x, and if y equals f of x, then the derivative could be expressed as dy dx, a ratio. If we allow ourselves to think of d as representing a small difference in some process, what in physics is represented by the symbol delta, then we're reminded that the derivative is simply the limit of ratios in the familiar form dy dx equals f prime of x is equal to the change in y values over the change in x values. This is our familiar average rate of change formula. It is the slope of the secant line. Similarly, we can read d dx as a single symbol meaning the derivative with respect to x of whatever follows d dx, which brings us to this new place of understanding the notation d dx of y or d dx f of x, the derivative with respect to x of y for f of x. The Leibniz notation can be a little cumbersome when you need to specify the exact x value where you need to evaluate the derivative. However, the benefit is that you can read so much more about the rate of change through this expression. It's very easy to write f prime of 3, but with Leibniz's notation, we will write the derivative format like this: dy dx evaluated at x equals 3. Here, we use this vertical pipe symbol to represent the point that we evaluate the derivative. Let's look at example 1. Here, Sean is cleaning out his saltwater fish tank and needs to drain some of the water in order to adjust the saline levels. If the volume of the tank V in gallons is being drained over time t in minutes, what is a meaningful interpretation of the following statement as it relates to Sean's fish tank? dV dt evaluated at t equals 3 is equal to -2. dV dt is a rate of change of volume. It tells us the volume that is flowing out of the tank per unit time. And so dV dt evaluated at t equals 3 would be equal to v prime of 3, which is equal to -2. And so that means that the rate is a negative number. This makes sense since the tank is being drained. So rate is negative to mean that water is being drained out of the tank. So after 3 minutes, the fish tank is being drained at an instantaneous rate of 2 gallons per minute. One other important point to make is that if we say verbally that it's being drained at an instantaneous rate, it would be incorrect for me to say -2. Negative corresponds to the fact that it's being drained. And so this would be a double negative. If we use verbs like filled or drained to describe the direction of the flow, then we need only give the absolute value of the rate of change in our description. Just like any other language course, we need to use proper names, spellings, and grammar conventions. In this sense, AP Calculus is no different than AP Language. There are many real-world functions that depend on variables other than x, y, or time. Learning to read and write the correct notation will help you succeed on free response prompts throughout our course. Now let's look at example number 2, part A. The Alberta tar sands are one of the biggest oil reserves in the world, yet extracting the fossil fuel costs more than the profits made. If the cost, C, in dollars, to extract a barrel of oil means that the company loses $3 on every barrel, write the derivative. So let's begin with our cost function. C equals F of B, where C is equal to cost and B is equal to the number of barrels. So now let's take the derivative. So the derivative of C with respect to B is equal to F prime of B. And this, in turn, will be equal to negative $3 per barrel. Notice that the units for our derivative are the same as the units in the original function. Now let's look at part B. The Deepwater Horizon oil spill is regarded as one of the largest environmental disasters in American history. The oil leak was discovered on April 22, 2010. BP originally estimated that the flow rate was about 790 cubic meters per day at the end of the first week. So let's take a moment and think about our units and when this derivative is going to occur. 790 cubic meters per day is our rate of flow, or our change in volume. And they tell us that this is the measurement, the instantaneous rate of change that occurred at the end of the first week. It's measured in cubic meters per day. So at the end of the first week, the amount of time that has elapsed would be 7 days. Let's write a function. So volume is equal to a function of time. Differentiating, we have dV dt is equal to F prime of t. And so dV dt evaluated at t equals 7 days would be equal to F prime of 7, which is equal to a positive 790 cubic meters per day. This is a positive rate of flow because it is an outflow. In part C, we're told the population P of the endangered mountain gorilla has an ongoing study tracking the number of gorillas since 1992. The population increased by 114 gorillas during 2003. So let's begin by writing our population function. P is equal to some function of time. P is population and T is time in years. Differentiating, we have dP dt is equal to F prime of t. This was a particular growth rate that occurred during 2003. And so what that means is that we're evaluating this rate of change for population at a particular value of t, the number of years that have elapsed since the beginning of the study. And so in this case, t would be 11 years. This is equal to F prime of 11. The population grew, so it is a positive rate of change, and the units would be gorillas per year. In example 3, we're told to suppose a planet is discovered in the year 2024 named Newtonia. If the alien population, P of t, is recorded in millions of aliens, and t represents the number of years since the planet's discovery, explain the meaning of each of the statements below. In part A, we're given that P prime of 3 is equal to 0.5. P is a population and P is a function of t, so 3 must represent the time, t, in years. So this would be 3 years since the planet was discovered. P prime is a rate of change in population as a function of time. And so this tells us that the rate of change in population 3 years after the planet was discovered is equal to 0.5. Now, what are the units for population? Millions of aliens. So this would be 0.5 million. So let's write this out. In t equals 3 years, or 2027, population on Newtonia will be increasing at the rate 0.5 million. So in other words, 500,000 aliens per year. It's increasing because this is a positive rate of change. Now let's look at part B. In part B, we're told that P inverse of 7.5 is equal to 5. So another way to think of this is that 7.5 is equal to P of 5. And rewriting it in this way helps us get our bearings on what the numbers represent. So here we can see that 5 is a time and 7.5 is the population. And so now we can write it from the perspective of our inverse function. Population on Newtonia will be 7.5 million aliens 5 years after its discovery in the year 2029. Now finally, in part C, we're given P inverse prime of 7.5 equals 0.75. So this is the derivative of an inverse function. So since the inverse function gives the number of years corresponding to a particular population, this represents the rate of change in the number of years for a particular population. So we can say when the population on Newtonia is 7.5 million aliens, it takes 0.75 years for the population to increase by 1 unit rate of change, which in this case would be 1 million aliens. In the previous examples, we've seen how important it is for us to make sure that our units for our rate of change match those in the problem. But in the next couple of examples, we're going to see how using units in the context can help us construct a rate of change. Let's take a look at example number 4. Suppose you launch a water balloon from a giant slingshot. Let S of t give the distance in feet that the water balloon traveled from its initial starting point as a function of time, t, in seconds. Explain the meaning of the derivative notation. Here we have ds dt evaluated at t equals 2 equals s prime of t equals 38 feet per second. And so to interpret this derivative, we can say that when t is equal to 2 seconds, the water balloon is... And so if we think about this, our ds dt is a rate of change of position. S is a position function, and so ds dt is a rate of change of position. And feet per second we definitely recognize as a velocity. And so we can say the water balloon is moving at an instantaneous velocity of 38 feet per second. So S of t is the position. V of t is equal to S prime of t, which is equal to velocity. Let's look at example 5. Here we're told the total cost of an airplane flight with n passengers can be calculated by derivative airlines using the function c equals f of n. What does it mean to say f prime of 182 equals 58? So c prime of 182 is equal to 58 means, and so since c prime is the derivative of c, this is going to be a cost in dollars per whatever the unit is that our function is. But remember that our function is actually going to be of the total number of people. And so this means that C prime is going to give us a cost per person. So C prime equals 58 means that when 182 passengers on a flight, then the cost per person for the flight is $58. So this is a very important calculation for a business to do, is to be able to find out the cost per person for the flight so that they know how to set their average ticket value. Finally, in example number 6, we're told that non-potable water is being pumped into a processing center where the depth in feet of the water at time t in hours is given by the function y equals h of t. Interpret the following statements using the proper units. H of 7 is equal to 5. So this would mean that the non-potable water is 5 feet deep after 7 hours. H prime of 7 equals 0.6. So this would be the rate of change of the depth. So the depth of the water is increasing or decreasing? Well, it's positive 0.6, so it's going to be increasing at the rate of 0.6 feet per hour at t equals 7 hours. In part C, we have the inverse function, h inverse of 7 equals 9. So this corresponds to 7 equals h of 9. So 9 is going to be hours, and 7 is going to be the depth at that time. So we could say that when the depth of non-potable water is 7 feet, then 9 hours have elapsed. And finally, we have the derivative of the inverse. H inverse prime of 7 equals 1.4. And so this is going to give us the amount of time required for 1 unit rate of change. So when the depth of the water is 7 feet, it takes 1.4 hours for the depth to increase 1 more foot.